I am Anil Kumar. Welcome to my series on trigonometry. In this video, we'll discuss cotangent function, its graph, and characteristics. If you want to learn from me, you can always send an email on the address given here. Please also check our website for the latest videos. I hope you have watched my video on how to graph tangent functions and their characteristics. Now, cotangent is reciprocal of tangent, so it's very similar to what we have discussed there. So it is a very short video, and I hope it will make sense since we have adopted few new techniques here, which we did not discuss in the earlier video on tangent function. So the knowledge of discussing tangent earlier and now cotangent will help you to understand this topic much better. We'll talk about the characteristics of cotangent function, the transformations, and the image points mapping. Graph of transformed cotangent functions will be taken as examples. We'll also write equation from the given graph. We'll be working with both degrees and radians, and the questions taken here are from previous test papers. Both the graphs shown here are the graphs of cotangent function. As you can see, most of the time they are in one direction. That means tangent by default is a decreasing function in its own interval. The interval in which it is defined is bounded with the vertical asymptotes. So the period between the vertical asymptotes is what we are looking forward to, and that is the principal cycle, which is the period from 0 to pi or 180 degrees. So we'll actually sketch the graph only in the principal cycle and then repeat it as we have done for the tangent functions earlier. Now let's begin with the properties of the cotangent function y equals to cotangent x. We'll consider the principal period between 0 to pi, which is 0 to 180 degrees, right? As such, you know that the period for the cotangent function is pi, right? So we know that the period is pi, or you can say 180 degrees, correct? Now, we are always talking about one particular period where everything will be analyzed, and that is called the principal cycle. This principal cycle will be from 0 degrees to 180 degrees. We cannot include 0 and 180 since they are not in the domain of cotangent function. At this point, we do have a vertical asymptote. Well, reason is very clear. Cotangent function cot of x is equal to cos x over sine x, correct? So we know that sine x cannot be equal to 0. So at 0 and at pi, sine x is 0. So therefore, it is out of domain. So we say that the function is not defined for the multiples of pi or 180 degrees, because since at that point sine x is 0. The function is always decreasing in its domain. So check each cycle, right? So in each cycle, it is a function which is decreasing from plus infinity to minus infinity. It goes through 0 at pi by 2, right? So the vertical asymptotes are at the multiples of pi or 180 degrees. It has odd symmetry. Odd symmetry, just as tangent function, cotangent has odd symmetry. Cot of minus x is equals to minus of cotangent x. X-intercepts are at odd multiples of 90 degrees or pi by 2. As you can see here, so pi by 2, 3 pi by 2, 5 pi by 2, these are the odd multiples where we are going to have the zeros. for the cotangent function. The y-intercept does not exist. In fact, the y-axis is a vertical asymptote. Now, it is important to understand that the key points which we are going to take up here, as we took also for tangent function, will be at a pi by 4 1, b will be pi by 2 0, and c will be 3 pi by 4 minus 1. So let me highlight these points here. We're talking about a, which is at pi by 4 and the y value is 1. Then we have the point which is the x-intercept at pi by 2, and then c, which is minus 1 at 3 pi by 4, right? So these are the three critical points which will be considered. The other 2 points will be approaching plus and minus infinity as x approaches 0 and 180. Perfect. So that gives us 5 things to consider. The other two, as I was saying, are the vertical asymptotes at 0 and pi, right? So this is our x equals to 0 vertical asymptote. This is x equals to pi, or you can say 180 degrees, correct? Or 0 degrees. So you could work in either degrees or radians, almost remains the same. So the principal cycle, as I was saying, will be considered for cotangent function between 0 degrees to 180 degrees or 0 to pi. Perfect. Now let's take an example. The very first example here is to sketch the graph of y equals to 2 times the cotangent function. So basically, it is a vertical stretch by a factor of 2. So the transformation here is vertical stretch by a factor of 2. So if you consider these standard points, as I was saying, A, B, and C, the key points, which are pi by 4, 1, pi by 2, 0, and 3 pi by 4 minus 1, then the y values will really get doubled up. The x values remain same. So the y values will be, in these cases, 2. Let me correct these values here. So at pi by 4, the value will be 2. At 2, it will remain 0. And at 3 pi by 4 is going to be minus 2. So those are going to be the image points, correct? So the image points, as we have shown here, for our principal uh, cycle, which is kind of right here. So that is the point which is B dash, that is A dash, and this is C dash, correct? So these are the three critical points. Well, the principal cycle is shown here between 0 to pi. So that is 0 and this is pi. So that is A dash, this is B dash, and C dash. So you can mark these points, right? And then we have vertical asymptotes at 0 and at pi, since as x approaches 0, the y approaches infinitely large. Twice infinity is also infinity. So it is the same uh, vertical asymptote. Similarly, at pi, we have a vertical asymptote where the graph is approaching negative infinity. So the points a dash, b dash, and c dash can be connected with a smooth curve which is decreasing within the interval 0 to pi. Now you can repeat this, right? So repeat the principal cycle, right? So to get the other graph during the domain, right? So that is what has been done here to produce the graph of cotangent function times 2, right? Where we have vertical asymptote. What you can also check here is that the point B itself shows you the translation. Now here there is no translation, therefore that 0 remains 0. The vertical stretch 2 is basically the difference between these two values, which we'll observe later, right? So that difference, this is the difference, right? Instead of one time, it has now become double, right? That is what it is. Now let's take up example 2, which is kind of similar. Y equals to half of cotangent half x. Now, if we have cotangent half x, then what is going to be the period? Well, in this case, the period will be double, right? So instead of pi, it is going to be times 2 or 2 pi, right? So that is to say, instead of 180 degrees, it is going to be 360 degrees. So this factor, which is shown here, which results into horizontal stretch by a factor of 2, increases the period. The vertical stretch becomes half. That is to say that the y value for the point A will now be A dash, the image will be half, not 1. So half of that. As you can now see, the difference between half and 0 gives you the value of the stretch factor A, correct? Okay, let's begin. So look at the transformations of the given function. We have a vertical compression by a factor of half and horizontal stretch by a factor of 2. So that means that the time period is doubled as the graph will be horizontally stretched by a factor of 2. So this time period which is shown here now is not pi, it is 2 pi, correct? So as you can see, from 0 to 2 pi, we have our vertical asymptote. So we have one vertical asymptote at 0 and the other one at 2 pi, correct? So that is what it is. The x values, they get multiplied by 2. Perfect. So getting back to our mapping diagram, the x and y will now become 2x and half of y, correct? So the point A, which is pi by 4, 1, will now be pi by 2 half, because that gets multiplied by 2, the x values, and the y values get multiplied by half. So it becomes pi by 2 half. Point B will now be at pi and 0, and point C will be at 3 pi by 2 and minus half. As x approaches 0, y approaches infinitely large value. In the image point also, it remains kind of same, right? As x approaches pi, y approaches minus infinity. And now, because this is horizontally stretched by a factor of 2, as x approaches 2 pi, it is approaching minus infinity. So you have a smooth curve joining the critical points A dash, B dash, and C dash, decreasing all the way from minus of plus infinity to minus infinity. Perfect. So that is how you get your graph, which can be repeated in the entire domain as shown here. Perfect. Now, let's take example number 3. I hope the concepts are absolutely clear. I'd like you to pause the video now and sketch the graph of y equals to 2 times cotangent half x minus 1. Let's look into transformations. Vertical compression, it should be vertical stretch by a factor of 2. So let me correct this. Vertical stretch by a factor of 2. Horizontal stretch by a factor of 2, right? So both are stretches in this case. And there is a translation of 1 unit down. Perfect. Now, how about the time period? Well, the time period is doubled in this case. So we have a period of 2, right? 2 times pi. So in this case, the period is 2 pi, or you can say 360 degrees. 180 times 2. As far as the mapping is concerned, x and y on the original function cotangent x will now be 2x, 2y minus 1. Minus 1 because it is vertically coming down by 1 unit. Perfect. So the points A, B, and C will now be transformed and their image will be at multiply the x values by 2 and the y values, multiply by 2 and take away 1. So when you do that, you get the a dash value as pi by 2, 1, b dash as pi minus 1, c dash as 3 pi by 2 minus 3. Correct? So when I do 2 times minus 1, it becomes minus 2. Minus 2 minus 1 is minus 3. So that is how we get minus 3. Now let us observe these points in the principal cycle, which is right here from 0 to, in this case, the pi, it becomes to 2 pi, right? From 0 to 2 pi. Now, within this principal cycle from 0 to 2 pi, we observe that the point B dash has moved 1 unit down, perfect, as it is reflected here. And this minus 1, you will observe, matches with the minus 1, which is the vertical translation, and that will always be the case. Perfect. So it will match the y value of b will match with the vertical translation. Now, as far as a value is concerned, a dash, right? So let us see a dash is at 1. Now, what is the difference? 1 minus minus 1 is equal to 2. And that is the stretch factor. Do you see there? By factor of 2. Vertical stretch factor. Since the y values, right, have been increasing. So this gap, vertical gap between a dash and b dash really reflects the vertical stretch factor of 2, correct? And the distance between the vertical asymptotes is reflected by the period k, correct? That is how you could actually relate them very easily. Now let's look into the end behavior, which defines the vertical asymptotes. As x approaches 0, y approaches infinitely large value. 0 times 2 is 0. Therefore, for the image, it is same. But when x approaches pi, y approaches minus infinity. That pi gets multiplied by 2, and we get 2 pi. So when x approaches 2 pi, y approaches minus infinity, correct? So that is how this principal cycle will be doubled. It will be from 0 to 2 pi, or you can say from 0 to 360 degrees as shown here. Perfect. Now let's look into the last example. Now in this particular example, the question here is to write the function from the graph, right? So write the function in this particular form, y equals to a cotangent x plus q for the following graph. So you are given the graph, and from the graph you have to write down the equation. I'd like you to pause the video, answer this question, and then look into my suggestions. So when you are given such a case, you should look for the critical points. So what are you going to look for? First thing which you should look for is the vertical asymptotes, and then what you should look for is the points A dash, B dash, and C dash. Perfect. These are critical points to look for. So let's see the vertical asymptotes, right? So what we see here is this is our first vertical asymptote, which is at 0. So first one is at x equals to 0. The second one is right there at 2. The other one is at x equals to 2. Now the difference between these two gives you the period. So 2 minus 0 is the period, and that gives you the value of k, which is equal to pi by p, right? So in this case, we know it has to be pi by p. Period is 2, right? Period is equals to 2, and therefore the value of k is pi divided by 2. So we get the value of k in the function, which is a cot of kx plus q, correct? So that is one way we got the value of k already. Now, what we are looking forward is the value of translation and the vertical stretch. Well, look at the point B. So if I observe the point B, which is this particular point, let's say B dash, the image, where is it? Now point B dash can be seen at 1, 1, right? So the coordinate is 1, 1. So clearly, this value 1 is equal to Q. It has been translated 1 unit up. Clear? So the value of Q is 1. Now let's look at the point A dash. Point A dash is right there, and the coordinates for point A dash are half and 3. Correct. To get the value of vertical stretch, that is the vertical distance between these 2 points. Correct. So vertical distance means difference between these two. So as we can see, 3 minus 1 is equals to 2. So the value of a should be 2. Substituting these values into our function, right, we get the answer. And therefore, the answer is that the function is y equals to, a is 2 for us, so 2 cotangent, right, k is half for us, we just calculated, right, and the value of q is 1, so we get 1. Perfect. So that is how very easily from the graph we can get the equation. Now here is the description which you should go through. Vertical asymptotes provide the period and the value of k. The vertical asymptotes are at 0, 2, 4, 6, correct? So those are the values for the vertical asymptotes. This indicates period of 2 for the cotangent function, and therefore k value is pi by p, which is pi by 2. Now compare the positions of the key points B dash and A dash. B dash is at 1, 1, A dash is at half and 3. Now point B is shifted 1 unit up, so Q is 1. You get the idea. So this point has shifted 1 unit up, this value, which matches with Q, correct? Point A is further 2 units up, which indicates vertical stretch of 2. You see that? Difference between the height of the y values of A and B gives you the stretch factor. Normally it is 1, but in this case it is twice, double. So the vertical stretch is of 2. Therefore, this particular function, which is y equals to a cotangent kx plus q, where we have a equals to 2, k equals to 2, and q equals to 1, will be what? Will be y equals to 2 times cotangent pi by 2x plus 1. Correct? So that is how we get the equation from the graph. I hope all the concepts are absolutely clear. But I'd like you to see this video along with the video which we have on tangent functions. So that will give you a clear idea of how should we work with tangent and cotangent functions. They go hand in hand. Perfect. So I hope it makes sense. Feel free to write your comments, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.